Can you see my screen?
Yes, sir.
So today's class will be a small class, short class, much shorter class than normal, but it will be pretty interesting actually. So, so let's start with. So, what have we done in this course so far? So we have seen different kind of algorithms, right? We have seen algorithms like say sorting, where we are given something and we have to do something on that, right? We have also done so many of these kind of stuffs were there, right? I mean, input is they have an input and you are supposed to produce an output. That output is a much more complicated stuff like that. But then there are also these things called these optimization problems. Say, for example, uh, like find the shortest path. Shortest ST path. Or find the MST. Correct? Or we had things like maximize the flow. And so on. So they are all optimization problems in the sense that you are given an input and there are I mean there is a lot of you have to output, okay? So output something that has a particular, there are two properties. Some it has some particular property. So like in this case, the property would be outputting a path from S to T. This is outputting a spanning tree. So this is outputting a flow. And also you want to optimize that quantity. Optimize the quantity. Optimize the measure. Then optimization meaning it's either mean or max. You try to come up with the shortest path, or you try to come up with the uh, minimum spanning tree. The spanning tree is the lowest cost, and so on and so forth, right? Now, today we will be looking at a slightly different problem. This is called what is called as decision problems. What are decision problems? So they are basically you have been given an input and the output is either 0 or 1, or you can think of it as yes or no. And the questions that are there are of a form that says that is there something? Now I can ask you some kind of we have done some of this kind of stuff. Say for example, is a graph connected? You just had to output is the graph connected or not? Yes or no? Right. Fine. But at the same time, many of these problems can also be written as a optimization, as a decision problem. Say, for example, for the shortest path, I can ask you this question. Okay. Is there a ST path of length less than t, less than or equal to t? I give you a parameter t and I ask you, is there a ST path of length less than or equal to t? Now, can somebody say how one can use this problem to solve this problem? No, sorry, T is not a good idea. I mean, so I made a mistake there. It's not the ST kind of T. It's like say D, some parameter D. Hello.
Sir, if this decision is 0 for all the paths, then it's the shortest path. D is the shortest path.
It is what is 0?
This decision, is there a shortest path of length less than equal to D?
Yes.
And D is that path.
Correct. But
Shortest.
okay, good. But but if I just say I have just given you an algorithm that you can give a graph and the D, and I will output yes or no to this answer. Using that, can you produce me a shortest path, or ask or not produce me a shortest path, but find out the length of the shortest path?
Yes, using that we can find all the paths from S to T and then compare.
You can find for all the paths from S to T. That's a lot of
No.
time, right? So you have to come up with some efficient algorithm. So I'm saying that, let's say that your job, your goal is to find the length of the minimum path, minimum ST path. Okay.
Then
But
we
what
can
you have been,
then we can vary
okay.
the parameter, right?
Yeah, we can. So you have an algorithm here. This is called what is called as the black box kind of stuff, where you can give a graph G and you can give a D, and the output will be either 0 or 1. Okay, and the answer is 1 if there exists a ST path in G of length less than or equal to D and 0 otherwise. Okay. Now, in that case, using this algorithm, so you have been given this algorithm, you don't want to go over and do a lot of complicated stuff. You want to use this algorithm, and without too much time, okay, you want to answer your own question. This question. Can you do that? Is the problem clear?
Sir, we will find the shortest path, say using Dijkstra's algorithm or something.
No, I mean,
and then compare
yes,
with
I completely understand that, but you are not going to say, I mean, this Dijkstra's algorithm is an algorithm that you know, right? But I can give you a much more generic thing. Okay, so forget that you don't have an. So this is an kind of a magical algorithm. Okay, it kind of does it very quickly. Can you use this algorithm to solve your problem?
We can
Sir,
give
we
some.
can vary the value of D, and we can check if there exists a solution or not. So,
How
like
will you
suppose,
take it? Yeah.
so suppose in the first you have given D and it
Yes.
says yes.
Yes.
Then I will change the value of D to D by 2, then
Ah.
check. So if it
Very
is
good.
no,
Excellent.
then I will check
So
some value
you can
between.
do, so if you know that this D, if you have an upper bound, okay, of the size of the shortest path, say maybe some of the edge weights of the graph, okay, in that case, I can use kind of a binary search to solve it, right? I can ask, oh, okay, does this graph has an, so I know the upper bound is at 1000, okay, I ask, is there a path of length less than or equal to 1000? Yes. Okay, very good. Is there a path of length less than or equal to 500? Yes. Wonderful. Is there a path of length less than or equal to 250? No. Okay, that's not good. So let's go up. Maybe I'll go with 250 plus 500 by 2. It's whatever, something 385. Okay. Is there a path of length less than or equal to 385? Yes. Then I will take 250 plus 385 by 2 and I go into the middle. And you can see in kind of, I can use this binary search algorithm to solve this problem. Okay. So this is in fact, maybe this is something was confusion that was created maybe to some people. What I am asking is that, okay, if I give you any problem, okay, so what is the problem? So I have a optimization problem. Problem. What does it mean? You have been given an input, okay, and the output is you have to output the max of some quantity. Okay, so now this some quantity is something not written properly, say max or mean or something. Okay, and the basic idea is that this can be, okay, what is the maximum vortex cover, or what is the maximum amount of material I can store in an abstract problem, or what is the maximum flow in a graph, or what is the maximum matching that I can find in the graph, and so on and so forth. Okay, so these are optimization problems. I mean, you can also have mean over there instead of max. And on the other hand, you have the decision problem. Okay, so decision problem is basically, again, you have been given an input, and your job is, and your output is that you can give a parameter D, and output is 0 or 1 depending on whether there exists this quantity with measure less than equal to D. So this is, doesn't matter whether you know how to solve this problem or not. Okay, maybe you don't know how to solve the max optimization problem, but you know how to solve the decision problem. That using the decision problem, you can solve the optimization problem using a binary search. Okay, is it clear?
Yes,
sir.
Oh, good. So in some sense, these decision problems are in fact the most well-studied problem in the whole of literature. Okay, because they are basically what can be done. It's like very easy to do it. Now there is also one trick about it, that even if you, after you find out the maximum quantity, okay, can you output the thing that produces the maximum quantity? That is not very clear. That is, you have to do it in a bit more hard work, right? So in some sense, if I tell you that, see, there exists a path of length, or the shortest path from S to T is length 100. Now, what is that path? Okay. Now, if you think a bit carefully here, just like you have changed this D, by changing this G slightly, you can do that. Okay. For example, I have a graph, right? Say here, I have a graph here, and I say that, okay, in this graph, S to T, the shortest path is 100. Now I want to find out whether there exists a path from S to T or not. So not whether there exists. I want to find out the shortest path. Can somebody tell me how I can use this one? Okay, so say that I have a black box. Okay, and let's just start with an optimization problem only. I will give you a graph, and you output this length of the shortest path path. Using this black box, can you find out the shortest path? Okay, so the goal is basically to find a shortest path. How will you do that?
Sir, initially, we can remove the edges that are incident on S one by one, and then check that what is whether.
Perfect. Very good. Yeah, I think you have got it. Yeah. So the main idea is that I mean, you don't have to remove one particular any incident on edges or not, but say I know that there is an edge over here. Okay, I will just remove this edge. So that's a new G. So consider the G prime, which is G minus E. Now, what happens if I fit this G prime to A? If this algorithm still says that, oh, see, this graph in this new G prime also, the shortest path is length 100. What do I know?
This
I
part
know.
is,
Sorry, go ahead.
Oh, means if the output is still yes, that the shortest path of length 100 exists, it means this edge does not belong to my shortest path.
Yes, or rather, there exists a shortest path that doesn't use that edge.
Yes.
Okay, so I can as well forget that edge, right? And since the graph is going smaller and smaller, after certain amount of time meaning the size of the input amount of time, I will be actually be left with only those edges that is required in a shortest path, right? And done. That's it. Is it clear? Hello.
Yes, sir.
Sir, don't we have to think about the time complexity of running it?
So there is a time complexity learning here. I will come to that soon, okay? But the main idea is that if you think of it, both the previous one and this one, meaning previous one meaning how to use decision algorithms to solve optimization problems, and how to use optimization problem to find the optimum solution kind of problem. Both of them are just polynomial time algorithms. The number of time I have to run this algorithm is at most polynomial in the number of input, because I will have to run it at most m number of times, right? But m is the total number of edges, right?
Yes.
So as long as all that you hear about is polynomials, okay, you are fine. So finding an optimum solution, okay, is basically same as finding the optimum value of the solution, is basically same as solving the decision problem of the solution. Okay, as long as you are not too worried about the runtime, is it a v square or v cube or v5, doesn't matter. But in terms of the polynomials, all of them are polynomials. Okay, now let me kind of go over this polynomial bit a bit. Sorry, this is something very essential. When I tell you that our algorithm, okay, when I tell you that, okay, here is an algorithm that given a graph G, that takes a graph G, or takes, no, sorry, so that has a polytime algorithm. Sorry, when I say that, okay, I have a problem, a problem P has a polytime algorithm. What do I mean by that? What does this statement mean? I've used this term many times, right? Can somebody tell me?
Not exponential, e to the power something, it's not like that.
Right, but what does it? It is
N to the power something.
It is, of course, cannot be e to the power something. But what it means is that, okay, what does it mean? Let me write down. So I will think of this polynomial problem to be a problem that takes the inputs okay, and make some output. Okay, doesn't matter. So that means there exists an algorithm that, what is it? That when given an input of size n, oh sorry, I made a big mistake. I will use this one. So there exists an algorithm, okay, A, and a number C, such that when given an input of size n, the algorithm correctly computes the P of the input, meaning whatever the output has to be done. Okay, so this is the output, correctly computes the output, and running time is upper bounded by, okay, see here, this C, n to the power C. Okay. Now this basically means that this C is a, look at this one. If you recall from your things from discrete math, so this says that there exists an algorithm and the number C. This number C and this number algorithm are not dependent on the input. So this C is a universal constant for this A. So for example, this C can be 100, which means that this algorithm for any input, if the input is of size n, it outputs in n to the power 100 steps, order n to the power 100 steps. Okay, if that C is, if the C is the 5,000, this says that this algorithm outputs in n to the power 5,000 steps. If the C is 2, then this says that this thing outputs in n squared steps, and that's it. Okay. Again, it can be any number, but this C is something that depends only on this algorithm A, and therefore there exists a particular C, a finite C for any particular problem, not for any particular problem, for if a problem is in P polytype, then there exists a particular. Okay, so note that one, what you are saying is that this quantity is not exponential. So this is not like e to the power n, because recall that, okay, this is something I hope that you guys remember, that, okay, n to the power C is much smaller than small o of e to the power n, or in other words, e to the power n is small omega of n to the power C. So that means e to the power n, or anything, or say any constant to the power n for that matter, say 5 to the power n, is way bigger than n to the power C for any C, constant C. Is this fine? Is this clear? I mean, 2 to the power n is way bigger than n to the power 1 million or 10 million, whatever. Now this statement doesn't make sense to you guys, possibly, for if you are not familiar with the concept of asymptotic notation.
I mean,
yeah,
for large
Hello?
n, right?
Yes, for large n, this is what happens. Okay, so this is something that is not true for big n, for small n's, but if you think that the n goes to infinity kind of stuff, then at some point of time, this quantity will be way more than this quantity. And this is what is meant by this polynomial, therefore. When we say that an algorithm, the problem can be done in polynomial time, then this is what is told. Now, a natural question that can come up in your mind is that why are we so much have a fetish towards this polynomial concept? Why are we like, oh wow, I mean, the polynomial is the thing to be. As you can see possibly that 2 to the power n, the n for which this quantity, this n to the power or 10 million or something, is smaller than 2 to the power n, that n is huge. Okay. But this is kind of historically what has happened. So in the early days, okay, so there are two reasons why one can think of this particular problem. Okay, in the early days of computing and all those things, when it was coming up, it was seen that the computers were becoming faster and faster every day, or every year the computers were becoming faster and faster. So what a computer could achieve, or a computer in say 1970 could handle only inputs of size 20. But a computer in 1972 could handle numbers of size for say 400. And if you think of it, the modern day kind of computers, they can handle inputs of size which goes into gigabytes. Okay, I mean there are supercomputers that can just easily solve gigabyte kind of solutions. They can use a human DNA and all and do the computations. So in some sense, if you design a program or write a program or design an algorithm, right? You expect that that algorithm should be in use for quite some time. So while at this point of time that an algorithm might not be doing very well, with a little bit more extra power in the computer, that algorithm will do very good. So in other words, what it says is that if for some small n in 1970, this number was way better than this number, because anyways, these computers cannot handle n more than maybe 10. But now with the n, now the computers can handle n which is way larger, right? And still, so therefore, this number, so n is huge, so this number would become way smaller than this number. And so the asymptotics come in. So when our job is to design algorithms, we should not judge our algorithm based on how it is performing in the modern day computers. We should judge them independently of any computer as such, right? And we should judge them as a limiting case. What happens eventually? And then it was found out that eventually this polynomials seems to be the most perfect thing to look at. Okay, and that's why we have got such stuck with designing algorithms that are polynomials. This is one particular aspect of why we are interested in polynomial time algorithms. Okay, I must say that there are, of course, you can design, you can define concept of exponential time algorithms and any time algorithms, but I will not be going into that in this class, in this course at all. So let me start with the formal definition of this class P. So P is the set of language. It is the okay, set of decision problems okay, for which there exists a polytime algorithm. So if you have heard of somebody saying that this language is in P, this is what they mean. It just means that there exists a polytime algorithm. It doesn't say that whether the algorithm is n square or n cube or n to the power 100. It just says it's a polytime algorithm. Okay. I mean, it's a different issue that some algorithms are, some algorithms are so bad polynomials that they cannot be used in practice. But that's fine. That is not what we really, or nobody looks at. Okay. I mean, if you ask different people in different areas of computer science, and they will say different concepts of what is implementable or what is practical. People who work with cutting edge, many of this high computing machine learning stuffs and all, for them, anything worse than linear is bad. For some people, for other people who are working with some other small things, anything beta worse than quadratic is bad, and so on. But everybody in the computer science kind of accepts that this concept of P is kind of important. Is this clear? Is this concept of P clear? Hello?
Yes, sir.
Okay, good. So now let me ask you a simple question, okay? Okay, so so you guys have seen things like, say, the vertex cover problem. Have you seen this vertex cover problem?
Yes, sir.
Okay, so what is it? Can you just explain?
Yeah, so the minimum number of vertex that is there to cover all the edges.
Right. So you have been given these vertices and edges, the graph, and your goal is to find the minimum sized set S such that for all UV in the edge set, either U is in set S or V is in the set S. So at least one of them are there. It is something very similar to what was done in the problem of this tower problem, right? It is something that is used a lot in the by the media people nowadays. So you guys, all of you, I am sure, use certain kind of multimedia, not multimedia, certain kind of social media platforms, right? Now, if there is a group who wants to pass on an information to all of you, okay, so it's hard for them to do it, right? Go and send individually, so that will go into spam. But instead, they would try to possibly target a few nodal people who basically are connected to all of, so all of us are kind of connected to one of these nodal people. And so find out the minimum number of people where I need to target to pass on that information is the solution of vertex cover. A vertex cover is a very important problem. You have, the tower problem is a problem with that. Okay. We also had this kind of the knapsack problem. You remember that knapsack problem? You have been given a set of items, right? So items I1 to IN, and each of them has a particular volume and a particular cost, and you have been given a sack of size S, okay, of a sack of volume V. Now, question is that you want to store as many amount of items as you can, such that the volumes are bounded and the costs are also maximized, right? You also have this ILP problem we have discussed a long time, for quite some time, right? So you have been given an integer linear program, and you want to solve that. So there are many of these problems, okay? They are all maximization problems or minimization problems. And you can consider the decision version of all the problems. Now, this question is that, are these problems in P? Okay. So is IL is say vertex cover in P? Is knapsack in P? Is ILP in P? So when I say P, of course, the P is only defined for the class of decision problems. So you have to consider the decision version of the vertex cover problem. So vertex cover decision version will be given a graph G and the parameter P. Is there a vertex cover of size less than T, right? And so on. So these are the kind of the questions that we like to ask. And I must tell you that this problem has been looked into by a lots and lots of people. There are quite more problems. Like you have heard of these problems of Hamiltonian path. Is there a Hamiltonian path? So is this in P? You might have heard of something called a traveling salesman problem. Is this in P? You might have heard of this very important problem, right? That given this is called a factorization. Particularly people coming from the cryptography must have heard this one. So I'll give you an integer. So what is factorization? I will give you an integer n and k, and the ask is that does there exist a number m which is less than or equal to k and m divides n? Okay, so not equal to 1. So this is the factorization problem. So many of these problems, unfortunately, actually all of these problems that I told you, they have been open for long time, really, really long time. And we have not been able to answer any of them. Okay, so till now we have seen things like, oh, this problem we can solve it in this time, this problem we can solve it in n squared time, n cubed time, and so on. But here we are asking, can you solve the vertex cover problem in some polynomial time? Yeah, we don't know. It seems like a very important problem. We don't know how to solve it. Can you solve ILP in polynomial time? Again, I have no idea. Can you solve factorization in polynomial time? Once again, I don't have any idea. And this has been quite a lot of things, problems. I mean, these are very, very important problems. They come up in real life applications all the time. And what it means is that if you don't have polynomial time algorithm, the best algorithms are exponential, or at least they are not polynomial, which means that they are not, in the worst case, their running time is not feasible in real life circumstances. So when people were trying to understand this set of problems, okay, this came up in the early years of 1970. Two gentlemen called Cook and Levin. One was an American Canadian, other was a Russian, and they looked at this set of problems. The concept of NP seemed to be, this P seemed to be very nice. But then what they realized is that there is some difference. For example, there is a difference between, say, this problem and this problem. Okay, what is the difference? Say, I go to you, okay, and I tell you that, see, I have this problem. Here is the graph, and I'm asking, is there a vertex cover of size less than k? Okay, and you say yes, it has. But I am not a fool to accept whatever you say. So you have to give me a proof. You have to convince me, right? How will you convince me? So this can be called, sometimes called, you can phrase it in terms of what they will have, this Akbar and Birbal kind of stuff. Okay, or you can write it as a teacher and student. So say they give this, they ask the question, okay. Sorry, does graph G have the vertex cover of size less than or equal to k? What does the student answer? Student answers yes. Okay, very good. You have got the answer. But now my question is that I am not accepting it. Why? Prove it. How will you prove it? Think about it. If I give you a graph and ask you to prove, and you claim that the vertex cover is of size less than k, how will you prove that thing?
Like
Any idea?
Like
Yeah.
earlier we did one problem, right? From decision problem to finding the
Yeah.
length of the minimum ST path. Then
Right.
from that to getting a,
Right.
actually providing a ST path, right?
Hmm.
So similar sort of thing.
But see, there is a difference.
But they are
Okay.
provided the algorithms, right, to us.
They have provided the algorithm. No, they have not provided any algorithm, but more importantly, they are cheating. They might be cheating. That's the main idea. See, I am a teacher. Think of my situation. I have asked you, given you a graph and told that, is this graph has a vertex cover size less than 4? All you have given is that you have told yes or no. That's it. And I have no idea whether you have got it or understood it. So you have to convince me that whatever you have managed to get is correct. How will you do that?
Okay.
It is easy, by the way, very easy, I must say. I mean, asking this correct question is the right thing. The hard one. Anybody else? Is the problem clear? Hello. Hello.
So just give an example of a vertex cover which is less than k.
Exactly. But okay, before I get that here, is this problem clear? Nobody answered it. Hello, this is very important. Is this
Yes,
problem
sir,
clear? I'm again asking.
Yes, sir.
Problem is clear, right? Anybody has any doubts about this problem?
No, sir.
Okay, good. So the answer to this one is that, I mean, the student or Birbal, whoever it is, can just provide a vertex cover. I have given you a graph and asked you, is there a vertex cover of size less than k? You just give me a vertex cover of size less than k. So what is the vertex cover of size less than k? Remember this, the definition. So the vertex cover, that means you have to give me a set such that this satisfies. You give me that set, and you give me the set such that the size of the set is less than k. And then I cannot solve the vertex cover problem, but I can check whether the given instance is actually a vertex cover problem, or in other words, is this one satisfied?
Verifying it.
I can verify it.
So verifying in what amount of time?
Yes, how much time will it take to verify it?
Like, n square time.
N square time?
Yeah.
I mean, again, in today's class, I don't care about n square or it can be verified in polynomial amount of time. Okay. So this is interesting. Answer, the student can give a small proof. So in this case, while I don't know how to solve the vertex cover problem in polynomial time, but if somebody gives a solution, I can verify that solution in polynomial amount of time. Same is for knapsack, right? You give me what all things to put in the knapsack. I check whether it satisfies the that all the volumes of the stuff that have been packed is less than the volume of the sack, and that's good enough for me, right? I realize that, oh, good. So here is a set of here is a set of items to be picked up in the knapsack that can be tested in that can be fit into the stack, and we can take this much. So this brings us to another very interesting problem, or not problem, a class of problems. This is the set of all problems, all decision problems for which, given a solution, for which okay, so what is it? Maybe I should write it here. Okay, so decision problem P such that if an item X is in P, meaning if the X, so when I say X is in P, that means this, I mean that P of X equals to 1, okay? So if X satisfies the property, okay, then there exists a polycized witness R of X and a polytime algorithm A that can verify if X is in P or not. So this is a very, very, very important class. Okay, so this is something that you guys might want to spend a couple of minutes thinking of it. Okay, so these are the set of problems that I'm not claiming that can be solved in polytime algorithm. But if an input, if an instance of the problem actually is in, I mean, evaluates to 1, or that means it is in that problem, right? Then one can give a short proof. And using that short proof, the verifier, or there is an algorithm that can quickly check whether the short proof is indeed an answer to the proof or not. Is this clear? Should I repeat it? So these are the set of problems for which verifying a solution is easy.
So this algorithm A takes Rx as input, right?
A takes X and Rx as input, both.
Oh, both. Okay.
X and Rx. It takes the input X and it also takes the input R of X.
Okay.
The not input, the witness.
Yeah.
So think of the vertex cover. It takes the graph and it takes the actual vertex cover that has been given to me. And all I need to check is that that vertex cover is indeed a vertex cover, and that vertex cover satisfies the property that it is less than k, the number of vertices are less than k, right? So then the subtle change that happened here, we are not talking about what can be solved, but it is then what can be checked, verified in polynomial time.
Sir,
Yeah.
sir, if px is equal to 0, then also
No, good, very good point. If p of x equals to 0, then I'm not guaranteeing you anything. It is only when px equals to 1 am I guaranteeing you something. Okay, if px equals to 0, so think of it that Birbal and the students kind of the job is always to convince that px equals to 1. Okay. So I have a x and I want to check is x in P or not. And you kind of want to say, yes, 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 it is in P. Okay. Now, if x is not in P, then of course you will not be able to convince me. But there is no guarantee that you don't need to convince me that x is not in P. It's like if I ask you that prove a theorem, what do? You give me a proof, I verify the correctness of that proof, and okay, good. So that means the theorem is correct. Right? I have not solved the problem. Okay. Or say I give you a question in your mid-set. Okay. I don't know how to solve it, but I've asked you. You guys have given me a solution to that. Okay, I can now verify whether the solution is correct or not by going line by line. Very good. But if the problem cannot be solved, then you will not be able to give a solution to that. If the problem that I asked was actually wrong, right? You will not be able to prove that's a problem. But in that case, you are not necessarily needed to even prove that the problem is wrong. Then you will get full marks. Okay. So as a student, your job is only when the statement is correct to give the correct proof. Okay. If the statement is wrong, I mean, you should not be punished for that. But if the statement is correct and you try to bluff and say, oh, yeah, it is true, correct. Obviously, it is true. I'm not convinced. You have to give me a formal proof of it, right? So if the X is in P, only then I insist that there has to be a small proof or small witness that X is in P. And that can be verified quickly. Is this definition kind of clear? Should I repeat it? Hello, how many of you have seen this definition before? Can you please unmute yourself and say yes or no? I'm not getting any feedback from the other side.
No, sir, I have not seen.
You have not seen. What about the others?
No, sir, I have not seen.
No, sir, I have seen.
No, sir, I have not seen.
I mean, this definition is not covered in our automata theory course, sir. Like,
This definition is not covered in automata theory course?
I mean, verifier part is not covered. Yeah, this definition is not covered. Rest of the things are covered.
Okay, but is this more or less clear what has happened? I mean, you have to think
Yeah.
about it quite some time because this is a very almost a philosophical level discussion.
Please clear, sir.
But this is exactly the class NP. What is NP? NP stands for, it doesn't stand for not polynomial. So you should not ever say the NP is not polynomial. It is called non-deterministic polynomial time. By apparent improvements. Okay, so it is non-deterministic polynomial. So that's why NP. So why non-deterministic? If you guys have done automata theory, how many of you have done automata theory? Or how many of you have not done automata theory? Can you please, whoever have not done automata theory, can you unmute and tell me? Shout out. Okay, all of you have done. In
Actually,
that
sir,
case,
Not done, sir.
okay,
sir, the course is going on now. I mean,
okay, the
so-
course is going on. Whoever
Yeah,
told not done, you have not even registered for that, or you're not finished that course.
Not registered.
Okay,
Not finished.
sorry.
Not yet finished, it's going on.
Yeah, not yet finished is not a problem. You have heard of this NFA, non-deterministic finite automata.
Yes,
What is that? You
Sir,
guess the path, right? And verify whether the path actually is the correct path or not. This witness is the guessing. These are the things in which you can guess correctly, then you can verify whether that correct guess is correct or not. Okay, non-deterministic finite automata is you guess a path and you do it. So if the automata accepts, then there is a correct guess, and you can check whether that path, whether the algorithm will get accepted or the string will get accepted by the automata or not. Right? In the case of NP, it is exactly same. If a language is in NP, then given an input X, if that X is accepted by is in the problem, is in P, in that language or in that problem, right? then you can guess the witness. There is a way of guessing the witness, such that after I guess it correctly, I can verify that the algorithm that indeed X is in P or not.
Can you
So now-
stress up on the definition of algorithm here?
Sorry,
Can you give a definition of algorithm here?
I mean which algorithm? The
Like-
A algorithm.
No, not any. Yeah, the CA algorithm. Yeah.
So any algorithm that takes an input and output 0 and 1.
Well, like earlier you used finite automata and NFA, like
And so
in
finite
terms of
automata,
Turing machine, something like that.
yeah, in terms of Turing machine is exactly same.
So existence of algorithm is existence of Turing machine.
No,
Takes
existence of not
input.
algorithm. Existence of algorithm is okay. So this
That's what you
basically
said,
is
right? There exists a polysize witness and a polytime algorithm A.
Right. So in other words, there exists a non-deterministic Turing machine that accepts it. What is a non-deterministic Turing machine? A non-deterministic Turing machine guesses and does that. And if it
Yeah.
guesses correctly, it will check it.
Yeah.
Okay, so this algorithm A, you can think of it as the non-deterministic Turing machine.
Turing machine.
Okay,
Yeah.
and the RX or whatever that witness is the non-deterministic guess.
Yeah. Oh, RX is a non-deterministic guess. Okay.
So Turing machines or finite state, all of the concepts are same. Okay.
Sir, for this particular algorithm, can I say that it is only a NFA? I mean, if a NFA can have a verification kind of.
NFAs are very weak. Okay. I mean, NFAs are very weak algorithms. So this is actually the classical way of defining this is actually using that non-deterministic Turing machine.
Okay.
Okay. So NFA, finite state automatons are very weak computing
Then-
tool.
I kind
Yeah.
of did not understand why RX is a non-deterministic guess.
RX, somebody gives you, God gives you, Birbal gives you, right?
Okay.
So he's an
Student-
oracle.
Um,
And the other way of doing it is I will guess it.
okay.
So think of the non-deterministic automata. Okay.
Hmm.
So somebody, you can say that, okay, X is accepted by a non-deterministic automata if a student can produce a path that takes X to the final state,
Okay.
right?
Hmm.
There are many paths, and in which somebody points out that take this path and you will go there. And you go there and verify that, oh, yeah, good, I reached the final state. Right? So somebody gives you, that's the witness.
So this A is a non-deterministic Turing machine which verifies whether X,
Yes.
which takes as input X and RX and which verifies
Not
whether
X and
is-
RX. X and checks whether X is in P or not.
Yeah.
It just, so if you want to talk about non-deterministic, the R of X is basically the case.
Okay.
Okay. So if you want to talk it in terms of the non-deterministic thing, a language L is in NP if there exists a non-deterministic Turing machine that accepts that language.
But that's also in polynomial time, right? Like what does it
Yes.
mean by
Yes. Non-deterministic polynomial time algorithm.
Oh, non-deterministic polynomial time algorithm. Yeah. Okay.
Exactly. Okay. The non-deterministic polynomial time algorithm.
Fine.
Yes. So if you're comfortable with the Turing machine world, then
Yeah.
P is the set of all languages for which there is a deterministic polynomial time algorithm.
Okay.
And-
Get- Hmm.
And NP is the set of all languages for which there is a non-deterministic polynomial time algorithm.
algorithm which can verify whether
Not verified. What does non-deterministic
Okay,
Turing?
okay, you're giving another definition of NP
Yes,
and both these definitions are equivalent. Okay.
are equivalent.
Yeah, that is the definition you taught us in class. Yeah.
Whatever, you can choose whatever definition, but the main idea is not to memorize the definition, but to understand it.
Yeah.
Okay.
But I'm trying to see how the equivalence is there. But
You are not seeing that? Okay, think about the non-deterministic part of the Turing machine.
yeah. So
Okay, who gives you the non-deterministic?
oh, actually, Rx use the Rx times this polynomial will become non-deterministic, right?
Yes.
Yeah, fine.
Okay, so yeah, so I can say that this concept is very confusing to many people who have not seen it for the first time, or seeing for the first time, and even otherwise. So please go and try to read it, understand it, okay? And the big question here, so this is the open problem, big open problem. Okay, this is the open problem that you solve, you become a, I mean, you can, a lot of things can happen. I mean, you can become a millionaire, you can become a zillionaire, you can also be hijacked by the terrorist. Is that P equals to or not equal to, whichever it is P equal to NP? Okay, most people believe this is not. Okay, most people believe P is not equal to NP. Okay, and but this is the problem. So if P becomes equal to NP, then all the cryptography that you are reading now, they collapses, they disappears. Okay, all the machine learning algorithms and all that are all beautifully constructed, they becomes, I mean, super easy. And if P is not equal to NP, that's what people believe. And I mean, it will not cause any massive chaos in the world, but it would actually solve one of the most, the biggest mathematical question in the recent times. So in fact, if you are interested in history kind of stuff, so this problem is one of the, so the Clay Mathematical Institute, they have some 6 or 7 problems, which they consider as the big challenges for mathematics and related fields. This is one of them. P equal to or not equal to N. What is it? Okay. So I will stop here today. I would like you guys to go back and find out whatever books, Wikipedia, anything, and try to learn about this concept of NP and P. And try to prove that some problem is in P, some problem is in NP. Okay. Of course, there is a lot more to be done. And of course, I told you that we were talking about the reduction and all those kind of stuff. Of course, we will come to that. Okay. In the next class, we will start from here. We will start from the definition of P and NP and talk about some more important stuff. Okay. So all the definitions that you, so there are many definitions that are there in different way of writing it, different way of expressing it. And that is why this problem of this class of NP and P are so robust, that you can define them in multiple different ways. Okay. In fact, if you are in the world of quantum computers, even you can define NP using quantum computers. And they also become the same. So, I mean, this was one of the big questions that was asked by Feynman at some point of time, or that is related to a question that was asked, and was finally sorted out. So there are various different.
Actually,
yeah,
quantum computers are non-deterministic Turing machines, right? In a way.
No. They are completely different objects. So let's not go into that.
Like
Yeah.
instead of uniform.
No, they are not. So let's not go into that.
Okay, fine.
Yeah, that's a completely different thing altogether. Yeah. So yeah, quantum computers are completely different objects. But so I would like you guys to go back and at least read about this concept, P and NP. Okay. Now I must say here that although we don't know P is equal to NP or P is not equal to NP, but actually we know quite a lot about these classes. Some of it we'll learn in the next class, and that will help us to design algorithms. That's why we are talking about it in this class. And some of it which will be in the, something that goes into the world of complexity theory. So it is not like some other math problem which we don't know how to attack also. So this is a problem where we know a lot, but we don't know the solution. And the solution is possibly really far away. So we don't know how to solve it. And we also know, if I just want to kind of give a teaser, we don't know how to solve it, this problem. And we also know that all the modern technology, modern mathematical tools that we have in our hand, none of them will be sufficient to prove P not equal to NP. Yeah, so if you are surprised by how can that mathematical statement be made formal? Yeah, they can be done. It's a beautiful area. So anybody who is interested in this theory kind of stuff, so this goes into the study of complexity theory. Something that I don't know whether will be offered in ISI sometime soon or not. Okay, so in the next class, we will be starting from here and go into two different directions, into one direction, more algorithmic, and show what can we learn from these two classes, how that can help us in designing algorithms and the challenges that we will face in designing algorithms. Okay. Okay. Any questions? Any questions? Okay, so I am assuming that you guys don't have any questions. So in that case, let's stop the class now. Okay.